All right, so now it will be much less motivation and much more detail. So let's start with Hilbert space. So we're studying quantum mechanics. The stage on which quantum mechanics unfolds is called Hilbert space. So I'll give you the definition, which many of you are likely familiar with. So a complex Hilbert space is a vector space over the complex numbers. It has an inner product, so it's a way of pairing two elements to get a number. If you pair a vector with itself and take the square root, that gives you a number which can be interpreted as a norm. It satisfies the axioms for a norm. And we assume the Hilbert space is complete with respect to that norm. So what does completeness mean? It just means every Cauchy sequence, so a sequence of elements of H with the property that the distance between subsequent points in the sequence is converging to 0. Every such sequence also converges to an element of Hilbert space. Okay, great. Now, since this Hilbert space is over the complex numbers, note that although often for real Hilbert spaces or real vector spaces, you think of the inner product as being symmetric. So the inner product between x and y is the same as between y and x. For a complex Hilbert space, that's not true. If you switch the order, you must complex conjugate. So you flip. The star means complex conjugation. And the reason that we need that is that so if we flip x with x, so if I flip the order, nothing changes, but if it's equal to its complex conjugate, then that guarantees that the norm is real. So x with x had better be real. So this guarantees that. We're going to choose conventions where the first slot of the inner product is called antilinear. What does antilinear mean? It means that a vector in the first slot that's a linear combination, you pull out the scalars and complex conjugate them. So if you pull out the a, it becomes complex conjugated. But if it was the other way, if it was x with a y, then that's just a x with y. So you conjugate if the scalar is in the first slot. You don't if it's in the second slot. Okay. So I'll later introduce a different notation for this. So for the moment, I'm going to call this math notation. And the important thing to remember is that since this is an inner product, both x and y are elements of the Hilbert space itself, and not its dual space, which I'll define in a moment. Okay.
Hold on. You're probably going to talk about this at some point, but why is this a good stage on which to do quantum mechanics?
Yes, I will absolutely talk about that because this should seem extremely confusing at the moment right now. I mean, why is it that a state of a physical system is a vector? That's weird, right? We normally don't think of if I have a physical state of a ball in California and another ball over at Greg's house. Maybe they're balls that are moving in two different directions or something. I never think of saying, oh, I can take those two balls and add them, right? You can add things in a vector space. You never think about adding physical systems in quantum mechanics. A ball here plus a ball there doesn't make any sense. So this should be very confusing. And later I'll give an example of an experiment that forces us to confront the fact that in quantum mechanics you have to be allowed to add states. Good question. Okay. Other questions? Okay. Good. I will not state all of the axioms for everything that all the words I've used here. So I'll just tell you all the usual axioms apply for a vector space inner product, norm, blah, blah, blah. If I were a very Greg type person, I would say, a vector space is something which forms an abelian group under addition, and scalar multiplication, here by scalar multiplication, I mean multiplying by an element of the complex numbers in this case. That multiplication defines a ring homomorphism from C into the endomorphism ring of this group. That's a very short and pithy way of saying what a vector space is, but it's more common to list a set of axioms. So for instance, that multiplication distributes over addition, which is implied by this statement. But I don't want to talk about that. I want to assume you know what a vector space is and move on. Okay. So we're going to specialize to finite dimensional Hilbert spaces. So let me first comment about the infinite dimensional case once to get it out of the way, and then we'll forget about it. So when you first learn quantum mechanics in an undergraduate course, you typically think of infinite dimensional Hilbert space. And in particular, you restrict to separable Hilbert spaces. So those are ones which have a countable orthonormal basis, or equivalently a countable dense subset. And one way of writing separable infinite dimensional Hilbert space is as lowercase l2. This is a vector space of square summable sequences of complex numbers, right? So it's an infinite sequence of complex numbers z. All the z's are complex, and the sum of the norm squareds of these numbers converges. It's less than infinity. That's one way of representing this. You might say, okay, what about other infinite dimensional separable Hilbert space? There are none. So all infinite dimensional separable Hilbert spaces are isomorphic. There's only one. So if anyone ever tells you, no, I'm not talking about this separable infinite dimensional Hilbert space, I'm talking about this other one, you should immediately be skeptical, because they're only one. I mean, every statement about one realization of separable infinite dimensional Hilbert space can be perfectly mapped onto any other realization. So there's only one. Now, I should hedge that there was one point in the server when we were talking about bases for Hilbert space, and Tetra was saying, okay, let me think about this using a different representation called L2, capital L, which is square integrable functions. And I said, well, no, let me think about your statement instead in terms of L2, square summable sequences. And he said, no, I'm talking about functions, not sequences. And I found that very confusing because they're the same. They're different ways of saying the same thing. So I should hedge that I trust what Tetra says, so maybe there's a subtlety that I'm missing, but ordinarily, modulo that subtlety, I would say there's no difference and they're all the same. Okay. So with that out of the way, I'm going to totally forget all of the subtleties of infinite dimensional Hilbert spaces, because to talk about the relevant features of quantum mechanics, it turns out to be sufficient to look at finite dimensional Hilbert spaces, which means the Hilbert space is Cn for some n. So that's what we'll focus on. Okay. So here's the first physics fact. The state of a quantum system is determined by a ray in Hilbert space. What is a ray? Well, it's an element of Hilbert space modulo an equivalence relation where I can multiply by any non-zero complex number. Right? So two states are equivalent. If I have a state, I'll introduce this notation in a moment. If I have a state, psi1, and psi1 is twice another state, psi2, I view these as being the same physical state because they differ only by multiplication by a non-zero complex number. Okay, so that's a ray. We often like to eliminate part of this ambiguity to multiply by complex numbers, and to do that we will demand sometimes that states are normalized. So if you demand that the norm of a state is 1, this eliminates the ability to multiply the state by 2, because that would double its norm. That eliminates some of the ambiguity, but not all of it, because I still have the freedom to multiply by any complex number of unit norm, which we call a phase. So the word phase in physics means an element of the unit circle, a complex number of unit norm. So this thing, something on here. Z is e to the I theta. So there's an ambiguity to multiply by a phase, but that's not as bad as multiplying by any non-zero complex number. That's a state. Okay. So now if you've learned about Hilbert space before, I need to map some of the things that you've learned onto physics notation. So we will write an element of our Hilbert space H as a ket. A ket is an expression of this form. So it's a symbol enclosed by a bar and an angle bracket. Now, often I know math people, I was a math physics double major, and when I would talk to math people about physics and write kets, often immediately people will panic because math people like to be extremely intellectually honest and immediately declare whenever they don't understand something. So math people will sometimes be like, oh, once I see a ket, I'm extremely confused, I don't know what this means, and they decouple. I'm going to try to reassure you that there's nothing confusing about this. When I write ket psi in H, that is no different than writing, say, lowercase v is in capital V, where V is a vector space. All that I've done is decorate the symbol V with a bar and a bracket. That's it. There's nothing fancy about this. So to further reassure you, let me make a very explicit example. So C2, the Hilbert space C2, has basis vectors E1 and E2, which I've just written as columns. So nothing scary, it's just, I would normally write this as E1 and E2 with no symbols decorating them, and now I've decorated them. So as usual, you know that a general element ket V in H can be written as a linear combination of basis vectors. So here is that statement with kets. So it's just a column vector. Right? Nothing scary, that's all a ket is. Okay. So physically, this Hilbert space models the state of a single quantum bit or qubit, like the electron which we had that we transmitted in the prologue. So in that case, it's common to write the basis vectors E1 and E2 as ket 0 and ket 1. So if you see those, or sometimes they'll be written as ket up arrow and ket down arrow. So if you ever see ket 0 and ket 1, or ket up arrow and ket down arrow, just think about the unit vectors, if you like, x hat and y hat for C2. That's it. Nothing fancy about them at all. You will often sometimes see the words computational basis, which is, again, just a fancy sounding term for this particular basis for C2. And one point of confusion is that ket 0, which is this ket E1, that is not the 0 vector. So when we write ket 0, we mean this unit vector over here, 1, 0, and not the 0 vector, which has the property that you can add to it, and it's the same. So the 0 vector I usually just write as 0, abusing notation with the scalar 0. All right, nothing scary about this. Now, what about bras? So this bra-ket notation has two components. There's kets and there's bras. What is a bra? A bra is an element of the dual space. So we know from linear algebra that H star, also sometimes written, for instance, in Tom's papers as H check or HV, this is the dual space to H, which by definition is the space of linear functions, so functions from the Hilbert space H to the field C. Now, in any course on functional analysis, you will prove a result, which I will not prove for you, called the Riesz representation theorem. This theorem, again, sounds fancy, but the statement is pretty simple. Every element of the dual space, so every linear function from H to C, corresponds to a particular element of H itself, which I'll write as y sub phi. So this is in H, not H dual. So there's an element in H with the property that the output of that linear function, evaluated on any other element x in the Hilbert space, is exactly the same as the inner product between this distinguished element y sub phi and x. So I'll say it again with different words. This is saying the action of any dual vector, any phi in the dual space, can be reproduced exactly using the inner product with an appropriate element of h, a vector. Okay, so this is a sort of correspondence between dual vectors and vectors. For any dual vector, I can pick out a vector that reproduces it. Okay, so this is why we use this notation, the Bra-ket notation, where an element of the dual space is now decorated with the other angle bracket. So remember, if I write V, that's an element of the Hilbert space. If I write V with the other decoration, that's in the dual space. Why do we use this decoration? Well, this decoration suggests the way that you would evaluate an inner product. So if I write a bra phi followed by a ket x, by definition, since a bra is an element of the dual space, this symbol means evaluate that element of the dual space, which is a function, on the vector x. But that looks just like the inner product. The inner product, y phi, where y is the element whose existence is guaranteed by the Riesz representation theorem, that element y phi, inner producted with x, is the same. So the bracket notation kind of reminds you that a bra acts like an inner product. But let me be very explicit about this notation. This is the reason why I emphasized a few slides ago that in the math notation, both x and y are elements of h, not h dual. So the difference between the math and the physics notation is merely that when I write a bra and a ket with a bar between them, the one on the left is in the dual space. When I write the angle brackets but not with a bar, a comma, in the math notation, the one on the left is not in the dual space, it's in the Hilbert space itself. That's the only difference. In the math notation, it's an inner product of two elements in Hilbert space. In the physics notation, it's an element of the dual space paired with an element of the Hilbert space. And these are equivalent by the Riesz representation theorem. So there's nothing scary about this either. This Bra-ket thing is an inner product. Good, was there a question?
Is this representation theorem like the way that you show that the dual space and the actual space are isomorphic in finite dimensions?
You don't have to use this. I mean, you can prove that the Riesz representation theorem assumes that there's an inner product. There's an inner product between these guys. You don't need to assume there's an inner product to prove that a vector space is isomorphic to its dual space. In fact, a vector space in finite dimensions must have the same dimension as its dual space, and any two vector spaces with the same dimension are isomorphic. So that's automatic. The issue, if you take a categorical perspective to this, the category theorist would say, okay, sure, but the isomorphism between a vector space and its dual is not natural. You have to choose a basis to define this isomorphism. So a vector space is only naturally isomorphic to its double dual, but not to its dual. That's true about vector spaces. But for inner product spaces, this Riesz representation theorem gives a preferred isomorphism between H and H dual in the way that I've written here. So I have not chosen a basis to do this, right? This is a nicer way to demonstrate the isomorphism without choosing a basis. But I didn't need to do that because for any pair of vector spaces, for any vector space and its dual, there's already an isomorphism if you let me choose a basis. Good question, though.
Okay.
Good. Other questions?
Not really.
Okay. Onward then. So let me make them. It was a good question because it signals what I'm going to say next. So let me make that isomorphism we just said extremely explicit. And I apologize for being a little pedantic, but I want to emphasize this to the point that even if I say things many, many times so it bores you a little bit, I want it to be extremely clear what I'm saying. So first, let me remind you that if I have a vector, an element of the dual space, I can construct a linear map, an element of the dual space. So sorry, if I have a vector, an element of H, I can define an element of H star using that vector. How do I do that? Here's how I define my linear map. I take my y in H, and I define a phi y in H star by declaring that the output of that function on any input x is merely the inner product between y and x. That's a linear function, so it's an element of H star. So now I've shown you that given something in H, I can construct something in H star. On the other hand, by the thing I just showed you on the previous slide, I can go the other way. If I have a linear map, which is something in H star, the Riesz representation theorem told us that there's an element of H corresponding to it with the property that that phi that I started with evaluated on any x is an inner product between y phi and x. So even though these two equations at the top and bottom look the same, the interpretation is different. On the top equation, I'm thinking of y as being given and constructing phi y. In the bottom equation, I'm thinking of phi as being given and constructing y phi. But I can go in either order. So the point, which I'm beating a dead horse here a little bit, the point is indeed there's a one-to-one correspondence between elements of H and elements of H star. So we will reflect this in our notation. If I have two elements, one of H and one of H star, that are related by this isomorphism, I will write them with the same symbol, but with one as a ket and one as a bra. Right, so this is an element of H, this is an element of H star, and I've used the same symbol for them, so that tells you these map into each other under the isomorphism. So that's part of why this notation is nice. It makes it obvious there's an isomorphism because I can use the same symbol and just flip the decorations. So in addition to this, it's in some sense redundant because now we've seen that an inner product captures exactly the same information as a pairing of an element of the dual space with an element of H. These are two ways of saying the same thing, right? For any Bra-ket, I can write an inner product, and for any inner product, I can write a Bra-ket. So eventually, as we get to more physics stuff, I will prefer to write the Bra-ket with the bar instead of writing the explicit inner product because they're the same thing. But for now, just recognize that it's redundant. I can write it either way. Okay, so let me again be very explicit. So we're specializing to Cn, finite dimensional Hilbert space. And as we know, there's an inner product on Cn, which looks like this. This is the math way of writing it. The usual inner product between V and W is you just add up V star times W for each of the components of V and W in an orthonormal basis. So to be very explicit, if V has the expansion, V is the sum V1, E1 up to Vn, En, then all you do is sum all of the complex conjugates of those V's times the corresponding coefficients in the expansion of W. That's an inner product. So let me write the same thing with our new Bra-ket notation. So now it's just ket V is the sum of all of the Vi ket Ei, which is a column vector, just an ordinary column vector. Now the bra, which is the image under the isomorphism between H and H dual, will have all of these entries complex conjugated, first of all, because in the inner product, the guy on the left is conjugated. And we're going to write it as a row vector. So operationally, to go from a ket to a bra, you just flip a column vector to a row vector and complex conjugate all of the entries. Okay, that's a notational choice. So you might be asking, why do you choose to do that? Write your kets as tall boys, column vectors, and your your bras as long boys that are row vectors. The answer is that this makes it very easy to remember how the inner product works. Right? So if we choose this notation where a bra is a row vector and a ket is a column vector, then a bra-ket pairing is just the usual matrix product. So if I write a bra and then a ket, remember the way that we multiply, this is a 1 by n matrix and this is an n by 1 matrix, and the way that we multiply those is to take this times this plus blah 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 plus this times this, which is exactly the inner product, which in math notation is that. So it's very convenient. It reminds you of how the inner product works if you write these as rows and columns. Okay, now some more notation. We'll introduce dagger. This is slash dagger in LaTeX. Slash dagger is just the isomorphism I told you. Slash dagger sends vket to vbra and vbra to vket. Or in terms of our row and column vector, all the dagger does is it transposes a vector. By transpose, I mean it takes a row vector and flips it to a column vector, or vice versa, a column vector to a row vector. And in addition, it complex conjugates each entry. So we'll see when we get to the next act, I'm already almost 1 hour in, but we'll see when we get to the next act that there's a similar dagger operation for operators. And this procedure for the vectors looks very similar to that procedure for the operators. So if you view a ket or a bra as an n by 1 or 1 by n matrix respectively, all that we're saying is that the dagger operation, if you view this as a matrix where wn comma 1, if you like, is just the, that should be an n, it's the nth component of w, and v1 comma n is the nth component of v star, because it's a bra. If you just view it rather than being a vector as a matrix, then you can convince yourself that daggering is just flipping the two indices, I and j flip order, and you get a complex conjugation symbol. Okay, so that's why we introduce this notation. It'll be nice when we have operators because the same procedure will apply to operators. Okay, these are bras and kets. Now finally, to finish this act before moving on, I will beat the dead horse one more time and very explicitly show a calculation. So again, let's go to the computational basis for seat 2. The states are 0 ket, which is this guy, and 1 ket, which is this guy. Now let me define another state. I can define a state which is, say, I over root 2 times 0 ket plus 1 ket, which is this column vector. Kets are column vectors. Now, what is the bra? Remember, to go from ket to bra, I complex conjugate each entry and go to a row vector. So since there was an I and I complex conjugate, this goes to a minus I by the conjugation. And then each of these kets turns into the appropriate bra, which gives me a row vector. So that's this. Now, what does this symbol mean? This symbol, bra psi ket psi. That means take this element of the dual space, evaluate it on this element of Hilbert space, which again, this is evoked by our notation where we use row vectors and column vectors. So if I write this out in vector form, this will be minus I over root 2 times the row vector, 1, 1, times the ket, which is I over root 2 times the column vector. Now, I take my matrix multiplication between these two and get 1 times 1 plus 1 times 1 is 2. And then I have to multiply I over root 2 times minus I over root 2, which gives me 1 over 2, which is 1. That's how to evaluate the ket bra in terms of column and row vectors. Let's see the same calculation in terms of kets and bras. So let me write it out here. Well, I already have. So I take the minus I over root 2 times the row vector written in terms of bras. So these are the bras 0 and 1. I multiply that by this guy in terms of kets, 0 and 1. And then I just distribute. The 0 guy comes in and hits this 0, so that gives me this. He comes in and hits the 1, and I get this, and so on. And now these are orthonormal basis states. Orthonormal means 0 with 0 is 1, 0 with 1 is 0, 1 with 0 is 0, and 1 with 1 is 1. So I get a half times 2, which is 1, which matches the other calculation. So I apologize for the degree of hand-holding, but I want to, if nothing else, have you come away from this talk realizing that when physicists write these funny kets and bras with angle brackets, all they are doing is linear algebra or vector multiplication that you already understand, but using different symbols for it. There's absolutely nothing scary about it. Okay, that is the end of Act 1. So let me stop again